175,000 light-years away in the southern hemisphere's night sky in the constellation, Golden Fish is a truly massive object. NGC 2070 is an emission embolus, better known as Tarantu. This tomb is gigantic and is believed to be the largest tomb known to date. This image shows one of the brightest space objects observed by Earth. To this day, there is no astronomer who has not heard of this cosmic miracle. The Tarantula Nebula is now the birthplace of stars. Earlier, behind the same powerful observational equipment, it was thought to be one of the brightest stars in the night sky, ahead of the constellation Goldfish. Nicolas Louis de l'Aquille was the first to recognize his true nature in 1751. Also, recent observations with modern telescopes have shown that this cosmic object is not a star at all, but rather a star in the sky. The size of this space object is huge. Imagine that this dome is about 1,000 light-years in diameter. If the closest object to us were replaced by the Orion Nebula, it would cover a third of the night sky. It would be 60 times larger than our familiar moon. He couldn't tear himself away from such a picture of the night sky. This dome overlooks the Milky Way's companion galaxy, the Large Magellanic Cloud. This emission is a large region of ionized hydrogen from which new stars form. Sources of ionizing photons are young, massive stars. Large dwarf stars are also powerful sources of radiation, producing large cosmic dusts of interstellar gas and dust. This is a very interesting phenomenon. These objects are formed by the gravitational influence of Tumbula's giant stars. Under this influence, gases explode, thus forming bulk-like shapes. Some stars explode in supernovae, most of which are illuminated by X-rays. That's why the Tarantula Nebula is so bright that we can observe it with the naked eye. Of course, for this you need to go to the southern hemisphere, and to see the exact outline of this space object as well as to see some of its great details, it is better to bring a good home or semi-professional telescope. But the VLT survey telescope at the European Southern Observatory in Chile was able to capture this dwarf and its rich stars in great detail. Here, for example, you can see the cosmic landscape of various star clusters, glowing gas clouds, and scattered debris from supernova explosions. Tarantula Nebula is named after its resemblance to the venomous spider tarantula. Its central part is similar to its body and contains large and bright stars. The spider's legs are clusters of gases, mostly hydrogen. The region itself is filled with this chemical element, but this giant spider is really kind. Tarantula's legs hug one of the largest cosmic objects known to us, the star cluster NGC 2070, an active star-forming region, and at its dense center, R136 contains one of the largest and brightest stars. With the Hubble Space Telescope's unique ability to capture ultraviolet light, researchers have been able to detect monster stars in the R136 star cluster that are 100 times more massive than the Sun. It automatically studies the largest collection of stars we know of. This cluster was first known to contain massive stars 50 times more massive than the Sun, and a new study found that R136 contains at least 9 stars with a mass 100 times that of the Sun. Notable among them is R136A1, the current record holder for a massive star, which is 250 times more massive than the Sun and is considered the heaviest star in the known universe. Not only are the stars very massive, they are also very bright, about 30 million times the luminosity of the Sun. Astronomers were also able to study the emission of matter from these animals in the ultraviolet range. Over the course of a month, they emitted a mass comparable to that of Earth, which is 1% of the speed of light. With such parameters, it is believed that the flow of matter leads to a very rapid mass loss. Astronomers are still trying to explain the origin of such giant stars. These giant stars are thought to have formed from the merger of less massive stars in smaller binary systems. This cluster contains another interesting star cluster called Hodge 301, where at least 40 stars have exploded as supernovae, spreading envelopes of gas across the region. One example of a supernova remnant is a star cluster known as SNRN 157b, which contains the scattered star cluster NGC 2060. The cluster was discovered by British astronomer John Herschel in 1836, using an 18-inch reflector telescope at the Cape of Good Hope in South Africa. Outside the Tarantula Nebula, the famous supernova SN 1987A can be seen in its lower right region. A supernova was the first star observed by modern telescopes since Kepler's observations in 1604. SN 1987A's light was so intense that within months of its discovery in 1987, it emitted 100 million solar powers. But if you look to the left of this image, you can see another diffuse star cluster called NGC 2100, which shows us a collection of blue stars surrounded by red stars. This group was discovered by Scottish astronomer James Dunlop in 1826 while working with a 23-centimeter reflector in Australia. The nebula also contains the star cluster and emission embolus NGC 2074, another large star-forming region. If you look closely, you can see a dark, dusty structure in the shape of a seahorse. This feature is called the seahorse in the Large Magellanic Cloud. It's actually a long columnar structure 20 light-years across, which is almost 5 times the distance from our Sun to the nearest star, Alpha Centauri. This cosmic seahorse should disappear completely within the next million years as more stars form in the cluster, which will slowly sweep away these structures with radiation and winds. Yes, the Tarantula Nebula is special. It is huge and contains many interesting things. It serves as a cradle for the birth of new stars, and at the same time other stars end their lives in supernova explosions. This is a wealth of information, and invaluable information for astronomers. What would happen if a supernova exploded near Earth? There are actually 3 answers, none of them very comforting. But before we answer them, let's try to understand what a supernova birth is, and why, even if they are very distant, they can harm all life. Thus, a supernova star or supernova flare is a star that rapidly increases its luminosity, followed by a relatively slow decay. A supernova is observed post facto, that is, after the event and its radiation reaches our eyes. A supernova occurs when there is a change in the center or core of a star. The change can take 2 forms, and both lead to a supernova. The first type of supernova occurs in a binary star system. A binary star is 2 stars orbiting the same point. One of the stars, White 4, steals matter from its companion star. Eventually, the white dwarf accumulates an inappropriate amount of matter, and too much matter causes the star to explode. This is how a supernova is formed. The second type of supernova occurs at the end of a star's life. When a star runs out of nuclear fuel, part of its mass falls to the core. Eventually, the core becomes so heavy that it cannot resist its own gravity. The core collapses, causing a supernova star to explode. A powerful supernova explosion is the final stage of evolution, resulting in the formation of a new astronomical body, neutron star, or black hole in the universe. What kind of object a supernova transforms into depends on how the next stage of evolution proceeds. If the gravitational collapse is stopped by the internal pressure, a neutron star forms. Such stars are compact, with a radius of no more than 10 kilometers, a high density of up to 1 billion tons per cubic centimeter, and 2.5 times the mass of the Sun. After a supernova explosion, 2 types of neutron stars remain, pulsars and magnetars. The former is 10 times heavier than the Sun, and the latter is 40 times heavier. Pulsars rotate on their axis at high speed, creating an energy field, and the poles emit pulses of radiation. The strength of the magnetar's magnetic field is 50 trillion times stronger than that surrounding the Earth. If the mass of the supernova exceeds the mass of the Sun by a factor of 40, there is a 100% chance that the supernova formed after the star exploded. Black holes form as a result of gravitational collapse. When a supernova has a mass of 100 times the mass of the Sun or more, the probability of such an outcome is very high. Black holes attract an incredibly large amount of particles every second, quantities comparable to millions of Earth masses. Excess energy is emitted back into space as radiation. Such is the future of our nearest stars. Yes, it's a Betelgeuse star, 20 times more massive than our Sun. It is now in the red giant stage, albeit a long-term dead stage. Betelgeuse is one of the brightest stars in the sky. The red dot in the constellation. Orion continues to amaze with its mysterious behavior. At the end of 2020 it faded, but now it is back and has become 50% brighter in a few weeks. This is what led to rumors that Betelgeuse would explode. It's not hundreds of years, it's decades or even years. Eventually, when the star runs out of fuel, it will collapse under gravity and go supernova. What if Betelgeuse explodes now? Should we pack our bags and gear and grab a bloody guinea pig for the bunker? Yes, sometimes people start doing something when it's too late, and it's better to prepare everything in advance when the last star leaves the station. But how to find, what, and how to prepare? Because our life is full of surprises. So if it's Betelgeuse, we shouldn't expect much danger. Yes, it would be wonderful, but the earth would not be struck by a shock wave. The towers of heaven would not fall like matchsticks. The sea would not rise like a wall. And the inhabitants of the earth would not burn like the last day. Apocalypse. I'm sorry, Thanos. So what will we see? According to calculations, it should be the second supernova explosion. This means that Betelgeuse, to an observer in its own system, will briefly be 500 million times brighter than our Sun. Yes, indeed, it is blindingly bright. But of course we don't roll Betelgeuse. How bright will Betelgeuse be for us? Given the distance from Earth to the giant, calculations show that Betelgeuse will be about half as bright as the Moon. Betelgeuse will be visible both during the day and at night, but it will not be like the second Sun. During the day, Betelgeuse will appear as a large bright spot, larger than an ordinary star but smaller than the Sun. At night, Betelgeuse will appear as a large bright cloud, comparable in brightness to the Moon. Over the coming months, Betelgeuse will begin to fade, but will remain visible during the day for 6 months or up to a year. For another 2 years it can be observed with the naked eye in the night sky. Only then will it disappear. Unfortunately, not a single dome is visible around an exploding supernova at a time. That's a long time, so we'll have to wait a few more years before we see a spectacular dome around a once-dead star. Astronomers with their powerful telescopes will be able to see the star's outer shell sooner. Fact, the big boss in Betelgeuse is 642 light-years from Earth, so its supernova maximum will shower our planet with massless particles called neutrinos. Fortunately, they cannot harm us, because neutrinos are strange particles that have nothing to do with the world. Look at your right leg. Trillions of neutrinos from the Sun pass through it every second. You don't see this shower because neutrinos have almost no effect on ordinary matter. Every few years, on average, one neutrino from these snowflakes will pull away a poorly anchored atom in your body. History shows that at least a dozen supernova flares in the distant past have survived us unscathed, and some were not far from us. Researchers have even been able to study the effects of these fires, not because it's scary, but because it's fun. Yes, there are some effects. In particular, geological layers of the Earth corresponding to specific time periods contain concentrations of rare isotopes that could only be produced by gamma radiation. However, the number of these isotopes is limited to a few atoms per ton of matter. No one would have found him unless he looked as special as Indiana Jones. To this we can add the increased concentration of nitrous oxide in the Antarctic ice. By the way, far from serious science, publications appear in the press about the possibility of the extinction of dinosaurs due to a nearby supernova. Alas, they have no scientific basis, since there are no traces of supernova explosions in several million years and in dinosaur bones. But those supernovae were far away, so we're still here. What would happen if a supernova occurred in the near future? To begin with, it is good to understand what is close and what is far on the interstellar scale. Our nearest star, Proxima Centauri, is 100 times dimmer than the red Derby Sun. It's about 4 light-years away, and in any case, this star doesn't threaten us with a supernova, no matter how angry you are. The components of the same system are located a little further away, and stars such as Alpha, Centauri, and our Sun will not be able to complete their evolution in such a spectacular way. We had to look for heavy stars, but none of the ones around the Sun. Even the bright Procyon Alpha Minor is 1.5 times larger than the Sun. We are interested in stars 8 solar masses and heavier. They end the evolution with a celebration and fireworks. And one. In front of you is the double star IR Pegasus, located 150 light-years away, which is 4 times closer than Betelgeuse. None of the stars in this system can produce a supernova flash, but working together it can. IK. One of the stars in the Pegasus system is the white dwarf. The other has reached the stage of becoming a red giant. Over time, the evil dwarf begins to attach the upper layers of the giant to itself, increasing its mass. After reaching a certain mass, the white dwarf has a chance to go supernova, and they should take advantage of it. But by then, the IK Pegasus system will be at a safe distance away from the Sun rapidly. However, if it happened now, it wouldn't be long before we felt its effects. One day we will see lights comparable to the Sun in the sky. For the Sun and the supernova to be on opposite sides of the Earth, the planet may not have any nights for a month or two. The visible light and heat rays from the supernova will cause a significant rise in temperature on the planet, albeit temporarily, and the radiation background would increase several times, which would put each Earth in a long mission to the ISS under astronaut conditions. But still, the inhabitants of our planet will be protected from the direct radiation of the supernova. For a while, earthworms will avoid bright light, stay indoors and play Tetris, go outdoors only when necessary, and cover their face and hands with masks and gloves. These theoretical considerations are not meant to prepare people to face another quarantine. However, let's imagine that the supernova exploded only 10 light-years away. Here, the results would be catastrophic. The flash also forms radioactive iron that can cause the destruction of the ozone layer and the penetration of dangerous ultraviolet rays into the planet, which will cause the extinction of all life on the planet. Bunker will be given some time, but this too will pass. And yet we can be sure that supernova diseases do not pose a threat to humanity. The risk of giant meteorite impacts, global pandemics, climate collapse, and nuclear war is greater. Yes, there is a lot of fear in our society, sometimes unfounded and unfounded. Fear is the strongest ray that destroys us more than the strongest radiation. So we would like to have less fear in our lives, at least not fearing one beautiful universal spectacle, the supernova star. Consider our favorite gold. Its nucleus consists of 79 positive protons, so gold must spin at more than half the speed of light to keep electrons from falling inside. This makes them more massive and pulls them into narrower orbits with lower energy. In this configuration, the electrons do not reflect blue light, thus giving gold jewelry its characteristic glow. Physicist Richard Feynman is said to have invoked the theory of relativity to predict the end of the periodic table at element 137. His calculations showed that electrons in elements above 137 must travel faster than the speed of light to avoid collisions with the nucleus and violate the laws of relativity. True, recent calculations have eliminated this limit. Feynman viewed the nucleus as a single point. Let this be a ball of particles, and the elements can live up to about 173. These outliers may be atoms, but like strange creatures that can summon electrons from space. Relativity is not the only problem. Positively charged protons repel each other, so the more of them in the nucleus, the more stable it is. Uranium, with atomic number 92, is the last naturally occurring stable element on Earth. Each element then has a rapidly decaying nucleus, and their half-life is time. The time required for half of a material to decay can be minutes, seconds, or even fractions of a second. Atomic physics in the early 1930s seems to be a strange pattern. Nuclei in which the number of protons and neutrons is 2, 8, 20, 28, 50, 82, or 126 and were characterized by high stability or stability. This regularity was confirmed not only by physical experiments but also by analyzing the distribution of various elements in nature. By distribution, you can judge how stable an element is. Natural reserves of elements such as tin, which has 50 protons in the nucleus, barium with 82 neutrons, and steel, which has 82 protons in its nucleus, are much larger than those of their neighbors in the periodic table. At that time, these facts did not find any explanation, and physicists began to jokingly call such a number of protons and neutrons magic. It is fortunate that this discovery was not made during the Inquisition. Then it was also noted that if both the number of protons and the number of neutrons are equal to the magic numbers, the nucleus is characterized by a particularly high stability. An example of such a binary nucleus is the isotope iron, 208, which has 126 neutrons and 82 protons. Current theory has succeeded in explaining the pattern of formation of magic numbers. Like the electrons of an atom, neutron and proton shells are formed in the nucleus of an atom. The structure of atomic shells is quite different from that of electron shells, but the most stable nuclei are isotopes with neutron and proton shells filled. Thus, a super-element with a twice-magic nucleus is predicted to be element 126. A doubly magical isotope of this element must have 184 neutrons in its nucleus. This magic number is theoretically calculated to be in the region of atomic number 126, so we will be seeing isotopes for a lifetime to study their properties. But how long such isotopes will live, days, months, years, cannot be predicted. Another area of stable isotopes is expected to be atomic number 114. Researchers face great difficulty in determining the properties of distant elements such as 114 or 126. Furthermore, there is no absolute certainty that there should be areas of stability. The most interesting search. If regions of stability are not found, current ideas about nuclear structure will have to be revised. If the prediction of the existence of new regions of stability of the elements is justified, it will open new perspectives for investigating the properties of transuranic elements as well as confirm the existence of the idea and make a great contribution to nuclear physics. Structure OF is the nucleus. Of course, heavier and more unstable elements may exist elsewhere in the universe, such as dense neutron stars. But for obvious reasons it will be difficult to study them directly, because you can quickly break down, adding to the table. But the good thing about modern laboratories is that they can achieve amazing results that unlock these chemical mysteries. Typically, new elements are created as follows. For example, we have a lighter atom called calcium. It accelerates and collides with a foil of heavier atoms. If an accelerated atom moves fast enough, its nucleus, the compact nucleus of a proton and neutrons in its center, can come into contact with the nucleus of one of the heavier atoms. If this is the case, they will combine to form a heavier element. Although a sheet of foil appears solid to the human eye, it is very different at the atomic scale. The nucleus occupies only a small fraction of the space occupied by the atom as a whole. And to create a new element, the nuclei of each atom must collide and combine. It's incredibly difficult. Here's why. If you imagine an atom about 170 meters in size, the center is a tiny grape. But there is another complication. If two nuclei are headed for a collision, they must overcome a strong repulsive force that prevents them from fusing into a new element. It is called electrostatic or Coulomb force. Only if the nuclei collide with enough energy will they overcome this force and eventually fuse together to form a new element. Let's call him Rudius. The theory so far predicts that new nuclei created in the lab will not survive long enough to form a real atom, because less than 10 trillionth of a second, a radioactive nucleus would not have time to collect electrons around it and create a new element. But things may work differently in space. The fact is that with high gravity, constant or changing temperature, new elements of matter can not only fill the table abundantly, but also reach a new level unknown to us. Yes, it is possible that black holes are composed of a complete set or nearly complete set of primordial particles that decay into energy, perhaps an indescribably fantastic conglomerate. For example, neutron stars, the precursors to black holes, are thought to have an upper mass limit of 3 solar masses. It is the maximum density of matter that is equal to the nucleus when all neutrons have all their quantum states, and these energies and forces of modern physics are known. But the combination of these energies could create something that is currently unknown to science.